amount of heat energy transfer during conduction. When a material slab is heated, material slab means it may be a stone heated from one side and the heat energy is transferred to another side. It may be our utensils used in kitchen. We heat here and the heat energy is transferred to this utensil. Okay, whatever it may be. What amount of heat energy transferred in conduction? We have a material slab whose one side temperature is theta 2 and another side temperature is theta 1 here. Okay, when this is heated, heat energy transfers from higher temperature to lower temperature, and here we have shown the direction of heat flow, and the amount of heat energy that is flowing across the slab is Q, and this Q is directly proportional to area of cross section of the slab. Okay, if the area of slab is more, the more heat energy transfer, and the temperature difference theta 2 minus theta 1, higher the temperature difference, higher the energy transfer, higher the time, higher the energy transfers, and this is inversely proportional with thickness. That means if the thickness of the slab is more, less amount of heat energy passes through the slab, and if the thickness of the slab is less, more amount of heat energy passes through the slab. In this way, we discussed in what parameters the heat energy flowing across the slab depends. Okay. Now the heat energy Q equals to Ka theta 2 minus theta 1 T by X, and here T. This T is coefficient of thermal conductivity. It actually describes the property of the material that says what type of behavior it shows for the conduction of heat flow. The coefficient of thermal conductivity may be more for some of the substances, and in those substances more heat energy flows. For some of the substances the coefficient of thermal conductivity may be less, and in those cases like cork, less amount of heat energy transfers from one side to another side when heated. Okay, now let's go. Thermal resistance. Likewise, we have electrical resistance V equals to Ri. In V equals to Ri, this is potential difference, this is electrical resistance, and this is current. This resistance opposes this current. In the same way, we have thermal resistance also. Let's discuss it. Okay, the law of thermal conduction is Q equals to A theta 2 minus theta 1 T by L. L is the thickness here. Okay, Q by T equals to del theta by L by Ka. Okay, now this is analog with the formula V equals to Ri. Here we say I equals to V by R, and here I flows. I is the flowing parameter, and here Q by T, we write it as Q by T is the flowing parameter. Similarly, V pushes I, V pushes I. Similarly, the temperature difference pushes the heat energy. That's why there is analogy between electrical resistance and thermal resistance. Okay, now H equals to del theta by R. Now this parameter L by Ka is thermal resistance. Okay, I flows, V pushes, R is electrical resistance. H flows, heat per second, H is heat per second. Del theta pushes, R is thermal resistance. Now rods in series. Now we are going to connect rods in series and parallel both, and are going to discuss what happens there. Okay, here we have two rods whose thickness is L1 and L2, and H1 and H2 are the heat energies flowing across the rods, and these two rods are connected in series as we can see here. Okay, now H1 we already studied. H equals to del theta by R. That's why H1 equals to theta 1 minus theta by R1, and H2 is equal to theta minus theta 2 by R2 in series. In series combination, like same current flows in series combination. Similarly, same amount of heat energy passes in the series combination. That's why right here H1 equals to H2 equals to H. Let's proceed further. Now let's add these two equations. We get H equals to theta 1 minus theta 2 by R1 plus R2. This is equal to del theta by R, where R equals to R1 plus R2. This is thermal resistance in series combination, and this is analog with electrical resistance R1 plus R2. In series, okay, total thermal resistance is equal to the sum of individual resistances. Okay, now here two rods are connected in parallel. Okay, when heat energy passes from this point, some of the heat energy goes in upper rod and some of the heat energy goes in the rod downward, which is downward. That's why we see here that the heat energy H is divided into two parts. H equals to H1 plus H2. H2. Like in parallel combination in electricity, total current I becomes I equals to I1 plus I2. This is electrical current, this is heat energy. And we see similarities between these two cases. Okay, let's erase it. H1 equals to theta 1 minus theta 2 by R1 and H2 equals to theta 1 minus theta 2 by R2. Here H equals to H1 plus H2. We add these two heat energies and get this expression. Here we see that 1 by R equals to 1 by R1 plus 1 by R2, which is same as electrical resistance connected in parallel. Now, these two rods are connected in series. These two rods are connected in series. And these two rods are connected in parallel. These two rods are connected in parallel and the conditions are given here: 100 degrees Celsius, 0 degrees Celsius. Okay, and in the first case, the rods are in series. In series combination, resistance in series equals to R1 plus R2. That's why it becomes 2R. Okay, rate of flow of heat in dq by dt equals to del theta by Rs. dq by dt is given 10 by 2. That's why it becomes like this. And R equals to 10 ohm. Similarly, in second case, the rods are in parallel. And in parallel combination, 1 by R equals to 1 by R1 plus R2. Rp equals to 5 ohm. Now dq by t, dt equals to del theta by Rp. For the second case, 30 by t equals to 100 by 5. That's why time becomes 1.5 minutes. Okay, here the thermal conductivity of given rod is K. Find thermal resistance. Now we need to find thermal resistance. We have the formula Q equals to Ka theta 2 minus theta 1 T by L. Now this becomes Q equals to del theta Q by T equals to del theta by, this becomes L by Ka. Now, heat energy passes from this point to this point, and in the heat or in the electricity, thickness is that one, that length, thickness is that length through which heat energy passes. Okay, here Z is the thickness, Z is the thickness through which heat energy is passing. Here R equals to L by Ka, and this L thickness is in our case is Z. And area, this is length and this y is breadth. That's why area becomes kxy. That's why r equals to z upon kxy, which is asked in the question. Okay, z upon kxy. This is thermal resistance between points A. Okay, now here is rod. We can see rod. One end is connected to ice at 0 degrees Celsius and one end is connected to water at 0 degrees Celsius. Okay, and the question has asked at what point along its length should a temperature of 20 degrees Celsius be maintained? We put this 200 degrees Celsius at a length x from steam or water so that in steady state the mass of ice melting be equal. Okay, When heat energy passes from this point to this point, ice here melts. M ice B equal to that of the steam produced in the same interval. Okay, when heat energy passes from this point to this point, water at 100 degrees Celsius changes to steam and becomes steam. And question has asked in which case mass of steam becomes mass of ice. Now let's find the heat energy flowing from this 200 degrees Celsius to ice, melting ice, and also find the heat energy flowing to water at 100 degrees Celsius from this midpoint to this, and let's equate these two equations and we get the required answer. The heat energy received by ice equals to Q ice equals to this much, and this heat energy that is flowing towards the ice, this heat energy that is flowing towards the ice melts ice, MILF. This heat energy melts ice. Mass of ice, melting ice, the heat energy received by water in time t, this much, and this heat energy that is being received by water changes water at 100 degrees Celsius to steam. That's why this expression becomes M latent heat of vaporization, and this M means mass of evaporating water. Okay, now according to question, mass of ice equals to mass of steam. On solving, we get x equals to 10.34 centimeter. Steady state. What is steady state? Whenever heat is supplied to the system, this is used in three ways. Actually, here it has become ID, but this is not ID, but heat energy is. This is. Sorry for this. Heat energy is used in three ways. Okay. The heat energy supplied is used in three ways. First, some of the heat energy is absorbed by cross section. Some of the heat energy is lost due to radiation and by convection. And some of the heat energy passes to the next cross section. In this process, when heat energy is passed for some time, in the rod, let's say this is rod. Initially, the temperature increases. This side, the air, in this cross section, the temperature of the different part initially goes on increasing, not decreasing, increasing, and after some time, the temperature becomes constant, not equal, not equal, but it becomes constant. And this is called steady state. And in steady state, the heat in ideal condition, the entering heat energy is equal to leaving heat energy. The heat energy that passes to the conductor is equal to the heat energy that is leaving conductor in steady state. Rods made of the same material and having same cross section are joined as shown. They have same length. The temperature of the junction is, okay, let's suppose the temperature of junction is theta. Okay, now this is 90 degrees Celsius, this is theta degrees Celsius. Therefore heat energy flows from this side to this side and this side to this side. The heat energy flowing from 90 to theta is, let's say, Q1, and from this side let's say Q2, and in this side let's say Q3. Q3 is the heat energy that is leaving the system, that is outgoing. Q3 is outgoing heat energy. Now just we studied in steady state entering heat energy Q1 plus Q2 equals to leaving heat energy. This is the key formula to solve the problem given above, and we solve it. Now first of all let's erase it. Okay, answer. Okay, incoming heat energy and outgoing heat energies are shown there. A is the area of cross section, K is coefficient of thermal conductivity of the rods, L is their length or thickness, whatever we say. Q1 and Q2 are entering heat energies and Q3 is outgoing heat energy, and in steady state Q1 plus Q2 is equal to Q3. Theta is the Now, okay, this is equal to Q1, this is Q2, and this is Q3. On solving, we get theta equals to Celsius. Here we can see analogies between thermal conduction and electrical conduction. For such videos, please follow our Facebook page, Physics with Physics. Your following helps us great and motivates also. And we kindly request you to follow our Facebook page, Physics with Physics.